been criticized for trying to explain or project the cost of something which is still a gleam in the eye. And I will try to justify this and say even though it is still a gleam in the eye, there are some conclusions that you can reach. I believe a somewhat similar set of questions applied to the possible development of fission fuel power plants in 1944. At that time, in 1939, fission was discovered. 3 years later, self-sustaining chain reactors were built and producing plutonium that was used in the bomb. So in 1944, I was aware of this and I asked myself, could this power be used in an otherwise conventional power plant? I asked myself this question, and the thought that I had was shown in the first slide, hopefully. Yes. This is a conventional coal-fired steam plant as was producing power at that time in the United States. On the left you see the firebox, which is burning coal to produce heat, which then goes over to a steam power plant where you have a turbine generator making electric power. You have a reject heat from the condenser. The heat firebox has fuel and air in, stack gases coming out, and ash also. What I reasoned was, next slide, I could take the nuclear reactor, which also makes heat, and also fuel goes in, ash comes out, and run steam to the steam plant. You'll notice that that box is in red. That shows that in that area there's radioactivity. My argument in comparing these two was that the power and energy contained in the nuclear fuel is so great that the fuel cost in the case of the nuclear plant would be trivial compared with the fixed charges. In the steam-powered plant, the cost of the fuel is about half the cost of producing electricity, and the other half is fixed charges. Fixed charges include a number of things. They include, well, the simple way of saying is everything but the fuel costs. That is the interest on the investment, the depreciation, the repair, the maintenance, the labor, taxes, insurance, and profits. So my argument was that the nuclear plant is not going to burn any fuel, or excuse me, the fuel costs are zero. So I'll take that money that I saved and I'll invest it in the increased cost of a nuclear reactor compared with the coal burner which it replaces. If then the fuel is half of the cost, I can spend twice as much on the nuclear plant as I did for the steam plant, the initial cost. And if the resulting cost is less than twice the steam plant cost, I'll break even. If it's less, I'll make money by changing to a nuclear plant. Let's look at the next slide. Yes. You probably can't see this, so I'll summarize it. These are construction costs of nuclear power plants in the United States. Over on the left, it names the company and the name of the plant which was built and the year completed. Numbers in there. The numbers in there tell Yep, that's good. Over here, I'll read some numbers. $145 per kilowatt, 164, 153, 181, 280. These are all less than twice the cost of the coal plant, which at that time was about $150 a kilowatt. So these plants, it turned out, did indeed produce electricity cheaper than the competing coal plants. However, an unprojected, by me anyway, thing happened. Here's the plants which were built in 82, 84, 85, 87, 86. The cost, instead of being less than $300 a kilowatt, is now $1,160, $1,880, $1,703. Here in 1986, one was built for $3,326 per kilowatt. A 22-fold increase in 15 years. At this time, nuclear power was no longer cheaper than coal-fired plants. As a result, no new coal-fired plants are built in the United States. However, you asked several things. First of all, I did not anticipate the added cost that was occasioned by the nuclear ash and the radiation produced in the efficient power plants. And the public acceptance of this was strongly negative, as a result of which there were increased costs, delays in licensing, and so on, which drove the cost up. Construction times, instead of being 5 years, became 10 years and more. And as I say, the nuclear plants were dead in the United States. I do want to point out two things. First, that the very simple assumption I made, that the fuel was cheap, did correctly predict what the cost of the power would be. And what the other element which came into it was the unexpected. I did not anticipate the added cost as a result of the radioactive ash. I suspect that the same thing would very probably be true in projecting the cost of fusion power plants, both hot fusion and cold fusion. It's also true that in France, it's been a very different story. In France, they were able to suppress or did not generate the same public bias against nuclear fuel. And at the present time, 75% of the public, the utility power is produced by nuclear power plants. And it has been true for some years, and the amount being produced is increasing with time. It's also true that in France, the cost of the fission power is about 20 to 25% less than the cost of the competing fossil fuel plants. Let's see. I would like, let's try the next slide. See what we got. Here is a projection made by Cohen in his book, The Nuclear Option. And again, it shows his projected cost of the future of coal down here as 4.8 cents per kilowatt hour. And here is his tomorrow's nuclear plant, 4.0 cents per kilowatt hour. He projects that the cost of the fission plant will still be cheaper than coal as for decades or so to come. Let's try another slide. And now, looking at thermonuclear plant with the DT reaction as the fuel. Here, we have a tokamak, or equal, fusion reactor. Again, we have heat coming out down here, going to, again, it's proposed to use a steam plant and turbines and so on. Again, we have electric power bleed to the steam plant coming back in, and we have tritium, which is extracted from the tokamak into a mixer in deuterium to make the fuel mixture. And this thing is a breeder. It puts out more tritium than it burns, so the tritium costs do not add to the cost of the plant. And we have also some decommissioning costs. The tokamak turns out to produce more neutrons per pound, per kilowatt hour of work than the existing nuclear plants. The only thing it has going for it is that it does not have the ash coming out that we are worrying about at the present time with the present nuclear plants. This problem, however, of the residual activity in the plant is avoided by several people that proposed, let's try the next slide, using, this is again, magnetic fusion energy power plant. Again, we have the nuclear reactor here. This is the same thing we had before, just a different picture. There's a blanket here of lithium in which the tritium is generated, but there is a flux of 14 millivolt neutrons going through the first wall. They have bad problems. One of them is they make the whole plant radioactive. And second, they I'll say mechanically, they destroy the properties, the strength of the material that separates the plasma from the lithium blanket. At the present time, it's planned that they'll have to replace that every 4 or 5 years. It'll be intensely radioactive. It'll take a year of downtime to do the replacement. And the replacement is all going to be done with robots, or Santa Claus is helping by remote control. Asking that we have no mistakes and no robots jam, as some of them did in the Soviet power plants already. That's, to my mind, actually a good deal. Now, let's try another slide. Here's one which, instead of using the deuterium tritium as a fuel, they use the helium-3. Again, we have to bleed power from the steam plant, well, at least to bring the stuff up to ignition temperatures and charge stuff in. It used to be that they, well, even if you have superconducting magnet coils, you still have to have, at the present time, refrigerators to keep the coils cold. This takes power, so you bleed off some of your output power to keep this thing going. If you look at this, you have a somewhat analogous situation with the cold fusion. Most of the plant's experiments do have electrolytic cells where you have power going in, and the excess power coming out, and most of them is only 30 to 40% of some such amount. If you put the numbers in, you'll find that in order to get an attractive output of power, the ratio of the output energy to the input energy has to be at least 10 to 1. And you're still taking a beating at that time. What else we got? Any more? Cold fusion, you see the similarity. We still have a lattice-assisted fusion reactor to make the heat. We have hot cooling coming out, cold cooling coming in, nuclear fuel going in, nuclear ash, and electric power. So to that extent, it's quite analogous to the hot fusion plant in terms of its plant setup. Now I think we'll be ending these parts here. There's more. There's been a lot of work done on the protecting the cost of hot fusion plants. This slide here shows over here the direct cost, capital cost of the plant in dollars per kilowatt. And there are tokamaks, a bunch of different ones over here. These all use the tritium deuterium. Over here I have one which uses the helium 3 deuterium. on the order of $2,000 a kilowatt. I'd like to make a projection here. What does this mean in terms of cost per power of the output? The answer is that if you add up all these items that I mentioned in the direct costs, you'll find that for every $1,000 that you have to pay for the plant to build, it's going to cost you about 3 cents per kilowatt hour cost coming out. That's assuming no other costs like the fuel are involved, which turns out to be true for all nuclear power plants. The fuel costs are relatively small compared with fossil fuels. Fossil fuels still 40% or more. In nuclear plants, it's less than 25%. A big item here comes how do you get this factor of 3 cents per $1,000 and so on. There's been a good. I can make it two. There are no more slides. I was thinking. Good. Here's the slides. I would like to see if we can put cold fusion into this picture. What properties does cold fusion have to be interesting in terms of this kind of action? The answers are, first, if you're going to use steam power plants, you'll find that in order to get a decent thermal efficiency, you're going to have the heat delivered to you at a temperature of several hundred degrees centigrade. Second, the energy output has to be at least 10 times the energy input to the cell or plant where it is. Anything more? Yes. The initial cost of the plant must be less than $2,000 per kilowatt. How can I hope that to project the cost of a cold fusion plant? It's really rather simple. We merely argue that compared with the hot fusion plant, with all of the whistles and bells and so on required, it's very hard to conceive of cold fusion costing as much. That's about as far as I can carry the costing now. There are a couple of other factors which I think are relevant, and that is I have compared this throughout with a conventional coal-fired steam plant. Coal-fired steam plant is no longer the cheapest source of making electric power in power plants. The cheapest source now is a steam-injected gas turbine. The steam plant has a thermal efficiency which peaks around 40%, and the cost at the present time is $1,500 a kilowatt. The gas turbine has a thermal efficiency of over 50% and can be turnkey delivered for $500 a kilowatt. So the cost of the electric power from the gas turbine, steam-injected gas turbine, is about 3.5 cents a kilowatt hour. There is one other reason for this is that the temperature in the gas turbine, instead of being 1,000 or so degrees Fahrenheit as in the coal plant, turns out to be 2,300 degrees Fahrenheit. And in aircraft gas turbines, they're now operating at 2,700 degrees Fahrenheit driven at temperatures. This trick is being presently proposed by Convair and the Russians. They propose to use, instead of the combustion in the gas turbine, a nuclear reactor and have a closed cycle helium to deliver the heat through the turbine. And they are again proposing that they will be able to produce power at 3 cents or so per kilowatt hour, which is going to be very tough to beat for the hot fusion plants or anything else. The only thing which is going to slow them down is in the case of the steam injected one, we're going to run out of natural fuels at the prices we're paying now, or the prices are going to go up, the cost will go up. In the case of the reactor heated, the reactor one is still condemned with the public bias against nuclear ashes.
Questions?
Can you hear me?
Yes.
Why, I appreciated your talk. I think it's very accurate. The question I have is what seems to be the high cost of palladium. Is that true? It would seem to me to make some of the palladium heavy water systems uncompetitive from an electric power generating viewpoint.
My feeling on that one is that at the present time, I, anyway, cannot tell you how much palladium is going to be required for kilowatt of capacity. I can't tell you how long it's going to last. And at this point, I'm not even sure that palladium is going to be the material used. It's a speculation. That's it. Any more?
Thank you. Well, just before the break, we'll have a very important gentleman, Dr. Robert Bass, who's a patent agent and member of the Science Advisory Board of ENICO.
Don't point that way to everybody's eyes.
Shouldn't you be wearing goggles?
Some people complain that the generals are always fighting the last war. And after I heard some papers the last few days, I think perhaps I'm fighting the last war. But I wrote this paper mainly for one person, Professor Peebles at Princeton University, who's just published a book on quantum mechanics with a 10-page section proving to his satisfaction that cold fusion is impossible by standard quantum mechanics. I'm not offended by him because he expresses puzzlement and he gives several comments to the effect, well, superconductivity was not predicted, but yet it's been shown more or less to be consistent with quantum mechanics. Perhaps cold fusion is something that we just didn't figure out right. So he expresses puzzlement, and I have sent him a paper trying to relieve his puzzlement. He wrote back and said part of what I had done, in his opinion, was valuable and should be published, but he remains of the same opinion still. So now I've got a new version, which I'm going to send him. And my real objective is to get him to agree that according to standard quantum mechanics, cold fusion is not only possible, but under the conditions that Fleischmann and Hans had, it's predicted as necessary. Now, in this abstract, in the abstract, I use the figure of 5.1 electron volts. Since then, I've made a more accurate calculation, and now I say 6.3 electron volts is the minimum energy of a deuteron traveling in a fully loaded palladium lattice that has, according to standard quantum mechanics, nearly 100% probability of fusing with one of the adjacent deuterons. So I'm going to try to show very quickly how I arrived at that. Now first, just consider the Coulomb potential of a fixed deuteron isolated in space at the point r equals 0. Then I factor out the, I think it's 5.08 is electron volts is this, E squared over L, where L is 2.83 angstroms in a fully loaded palladium lattice. And I make a non-dimensionless potential, which in this case is 1 over the absolute value of C, which is the radius divided by the distance between deuterons in a linear model. Now, this is the Coulomb barrier, which people claim cannot be overcome. And their calculations are on that. Now, the first improvement that we should make is not to consider an isolated particle, but to consider two particles, one in the dimensionless model at -1, one at +1. They're bound deuterons. And then we have between them, the repulsive forces make a potential well. And I assume they're isolated, so it just drops off forever, no other particles. And this is an improvement. And if you do this, you can arrive at two things which are worthwhile. You can arrive at the 0-point oscillation for a deuteron which is sitting there. If this is at 0 Kelvin degrees, that's what Schwinger studied. You can also find the energy levels of bound states. That's a quantized anharmonic oscillator. This curve here is like 2 over 1 minus c squared. That's this potential well. And if you apply standard quantum mechanics, you'll find the energy levels of the bound states. Now, I've shown 5 of them, but they're exaggerated. Really, they're between 6 electron volts and 7 or 8 electron volts. They're about 75 energy levels where you have bound states. Now, it says in the standard classical quantum mechanics book by Bohm that it's very, very remarkable that if you take wave mechanics seriously and you replace the situation shown here by one which the only modification is to make the situation periodic, then the energy levels of the bound states are no longer energy levels of bound states. They are the exact conditions for resonant transparency. In other words, a deuteron moving at that energy can just go sailing right through forever. Now, the first person who noticed that was a letter to the editor in Physics Today by Leif Turner. This was picked up by Bob Bush, and he's demonstrated it with remarkable experiments. I had an argument with Will Haber. I said there's nothing in all of science where something very complicated like Bush's curves have been experimentally demonstrated and then shown to be a mistake. He said, what about epicycles? I said, epicycles were correct. You just take Newton's solution, expand in a Fourier series, and the first 3 epicycles and the first 3 Fourier coefficients. So I believe that Bush has demonstrated the validity of resonant transparency. However, the way I'm doing it is more accurate than the way he did it, and I'm finding scores of resonant transparency energy levels between the energy levels that he found by a relatively crude calculation of the same type. I'm using the WKB method. Now, the first thing I did was to calculate the potential as an infinite series, and I calculated the first 44 coefficients, and you can see that they're converging to 17 decimal places on 2.0. So beyond the 45th coefficient, I just take them as exactly equal to 2. And the power series that I have expresses the following model. You have to include the periodicity of the lattice, or you're not going to find out what's happening. And in addition to the 2 deuterons that I showed, you're going to have a periodic array of deuterons, and then I put one negative charge representing an average position of an electron in between every pair of deuterons, so that what's on either side of the energetic deuteron is grossly electrically neutral. Now, this is the famous Madelung series. The Madelung series, normally the way they do it, it says in the Encyclopedia of Physics, it takes thousands of terms and you don't get very poor numerical accuracy. Well, in my paper, you'll see I've discovered a way to do the Madelung series that converges with just a few terms. In fact, I use 44 terms and I get 17 decimal place accuracy. And it's not just academic nitpicking to include the effect of all the other deuterons and all the electrons, because the potential well with the Madelung series is 39% deeper than the Coulomb well alone, which is what other people have been thinking about. Mostly, they don't even allow the other particle. They just look at one Coulomb barrier. But it's the resonance going back and forth between the two Coulomb barriers that are going to penetrate. Now, Dr. Kim is on the right track looking at the resonance in the nuclear potential, but I have to warn him, he's going to discover that when he does it I'm using an approximation, when he does it very accurately, he's going to find out that he can't penetrate the Coulomb barrier unless he gets up to MeV. So MeV doesn't help, but if you do it the way I'm doing, you can penetrate the Coulomb barrier with 6 and 7 electron volts. Now, here are the lowest 5 energy levels where the Coulomb barrier is completely transparent. According to the WKB approximation, it's exactly 100% transparent. These are, I just did the first 5 of them. This is non-dimensional. This is putting in, multiplying by 5.082 electron volts to many dimensional. See, I go from 6.3 electron volts to 6.9 electron volts with the first 10 energy levels. Then after 75 energy levels, I've gotten up to the point where it's equals 2. This is what you would get if you left out all of the other deuterons and all of the other electrons. Therefore, in a simple model where you leave out the rest of the lattice, you're going to have to go to the 75th true energy level before you even find anything. But if you have the type of model I have, you can find 75 different levels of resonant transparency where the Coulomb barrier effectively doesn't exist at relatively low energy. Now, I did the 88th and 89th one just because I wanted to see the difference between the two. It's 13.74, 13.85. Now, the important thing, which Bob Bush has called attention to, is the broadening of the lines of resonant transparency. He has in his paper some calculations that thermal vibrations in the lattice will broaden the lines. Now, I have what I consider to be a somewhat more subtle theory of the resonant line broadening, and I get tremendous broadening compared to what you will find, like 10 to the 100th times more than you will find in the book by Bohm that I just cited. And the way I get the line broadening is something that we've heard about lately from Bush yesterday and from Hal Fox. The 0-point vibrations. Now that was the beginning of Schrader's theory of nuclear energy in an atomic lattice. Consider this is the 6.3 electron volt deuteron. See, it will be left or right. And this is a rigidly bound deuteron in the lattice here and here. This is at plus L. This is at minus L. At L plus lambda and L minus lambda, there's a little oscillation interval where the lowest order solution of a quantized linear oscillator says that there's a Gaussian distribution of the location of the deuteron, even at 0 kelvins, at absolute 0. Now, I've called in my work the sigma in honor of Schwinger, the Schwinger ratio, L over lambda. Lambda is the amount that the deuteron is trembling in the lattice where the lattice is 0 degrees. Measurements show that the Schwinger ratio is 28. Now, in my theory, using the Madelung series, I get this simple formula where the only experimental thing I enter is 2.83 for the lattice period, and I come out with a Schwinger ratio of 22. Now, that's not as good agreement as one might hope for, but if I include, this is just a linear one-dimensional model. If I include the repulsive forces of the nearby palladium ions in the three-dimensional model, I'm sure I can get this up to 28, but I haven't done that yet. Now, people were objecting yesterday or day before yesterday, where Dr. Kim was talking about resonant transparency. They were talking about it takes longer than the lifetime of the universe to get through. Now, the way I'm doing it, it does not. You can read my paper, but I don't think I have time to spell out how the trembling at 0 kelvins of the rigidly bound deuterons broadens those lines. But anyway, just from Heisenberg's uncertainty principle, this is the second way that Bohm shows how to calculate the time to get through. Since I just showed you the lines, the very lowest line is 6.3 electron volts, the width of that line is 10 to the minus 3 electron volts. Therefore, by Heisenberg's principle, the time to get through the tunneling is greater than 10 to the minus 12 seconds. So we don't need to worry about waiting until the age of the universe has passed. In conclusion, here's my conclusion. To the extent that the WKB approximation yields qualitatively correct results in resonant transparency analyses, standard quantum mechanics does predict deuterium plus deuterium will give helium-4, and that probably depends on something I didn't say. I've solved the problem not only for the double potential well, but for the quadruple potential well, and I include the strong nuclear force. It can get through the Coulomb barrier, but it doesn't get through the nuclear force, so it will penetrate the Coulomb barrier, get in the vicinity of the rigidly bound deuteron, but not come out on the other side. So standard quantum mechanics predicts D plus D to helium-4 in a fully loaded palladium lattice if one of the moving deuterons has at least 6.3 electron volts energy. Now, my recommendation for future work is this, that the Madeline potential, which I defined by that infinite series, you can get 16 decimal place accuracy by taking 44 terms, and the remainder here is very small, but this reduces the error to 10 to the minus 100 or something. One should define and tabulate exact solutions of the Schrödinger's wave equation analogous to the Coulomb wave functions used by Kim, Yoon, Zubarev, and Rabinovitz in the paper they gave, paper T 2.2. I think they're on the right track, but they're doing resonance off of the nuclear strong force, and they're going to need MeV to get through. If they apply their model, which is exact, to the scenario that I showed, then they're going to find that you can get through at 6.3 electron volts, or approximately thereabout. Repeat the preceding resonant transparency level search using more accurate methodology of Kim et al. Instead of the WKB approximation in order to predict those resonant transparency levels. Finally, I would like to thank NECO for having sponsored this work. Yes, Dr. Bush.
Yes, that was a very interesting talk, Dr. Bass. I wish you'd talk to me about this guy, Yendel, who commented on my original transmission resonance model. I became convinced, based on a paper that he did, that you simply cannot get the transmission rates here that you need to get any meaningful diffusion. So this approach, I'm afraid, in my mind, has been established by Yendel as simply not being able to get through the Coulomb barrier. I mean, he does some very interesting work here, and maybe it will be useful for something, but in my own estimation, as somebody who started this, I became convinced that it would not work, and at that point, my transmission resonance model was a semi-empirical model that did not have a mechanism to get through the Coulomb barrier, but still was a useful model. And if you look at my light water paper, I have a different physical interpretation of it that still allows it to give you the hills and valleys. But I'm convinced, and I wish I could say otherwise, but I think it does some very creative work. I'm convinced that it does not get through the Coulomb barrier with the rate to get anywhere near what we need to get the proper amount of excess heat. I'm sorry to have to say that I think you've done a nice piece of work here.
I think you say that solely on the basis of integration. I want you to say that on the basis of a calculation. In my paper, I've evaluated all the integrals that are given in Bohm's book. I've evaluated them numerically. I've done them with 2 different computer programs on 2 different computers, and I get the same answer. And I stand by my conclusions, which I think are going to convince Professor Peebles at Princeton I'm going to send it to him. I've got all the details worked out. I've crossed every T, I've dotted every I, and I resist this suggestion that what I have done is not right. Because it is correct. Every last detail is there. I gave you my paper yesterday. You show me one error, please.
Well, I haven't seen your, I have not read it.
I gave you both papers yesterday.
Well, I have not read it. I thank you for giving it to me. I think you need to look at Yendel's paper.
Why don't you show me?
And I'd be happy to find you a copy of that for you. But basically what I'm saying, you claim to have improved on me, and I think that may very well be true, but I think that the same flaw that my model has, yours certainly has. I don't see any way
But show me the flaw. Show me. I've done it the same way that they do hundreds of experiments in nuclear physics that are in the black and white top book, in the book by book by Bohm. I've done it exactly the way these people have.
The flaw is it simply takes, you get into one of these, start the thing out of one of these wells, and it simply takes too long to leak
It
out.
doesn't take too long because I'm getting through with I'm getting through with
Yes, please continue this discussion
accuracy to 10
out
to the 100 decimal
in the
place.
back rooms or the hallways or something what have you.
It's not the lifetime problem.
Let me just say this. Any other questions?
Yes.
One quick, more
Can you
question.
discuss your proposal with Kim and Williams?
I gave Kim a copy yesterday. He just told me that WKB method is no good. I don't think he's ready. I don't think he's ready either.
You read Yendel's paper.
Nobody has shown me that.
Well, I think you need to agree. Yeah, I think
Well, if all he's doing is saying the lifetime is bigger than the universe, I know how to do that calculation. It's in Bohm's book. I completely get around it because the term that has to be bigger than life in the universe, I'm multiplying by something that's 0 to 10 to the 100th decimal place.
Bohm's book is very misleading. You need to go back and look at
There's nothing like a good fight between friends. Among friends.
it. We're still friends.
Yes, of course. Let me just say this. We're going to take a break now. We're running 10 minutes late already. I think we should come back in 15 minutes, which would make it, according to my watch, which is still on Eastern time here, 4 o'clock.
15 minutes after whatever your watch says.
Okay, but there are two.
If you can, come back. We have a gentleman that's asking for our help, and we need all the brain power we can get.
I wanted to say indeed that there are two speakers. There's Joseph Wokas, if I'm pronouncing that correctly, and James Griggs of hydrodynamics. I just want to say I don't know too much about Mr. Wokas, but I have seen a lot from Jim Griggs, and I want to put the strongest advice for you to come back and hear what Jim Griggs has to say. Thank you.
Can you hear me back?
Come.
Sort of.
Yeah. Good.
Because of improvements in the rates of understanding of cold fusion, we may soon have to look closer at possible nuclear proliferation aspects of cold fusion. Two major concerns about cold fusion and nuclear proliferation we'll examine today are: can cold fusion breed fissile material from available materials? And can cold fusion make a breeder out of natural unenriched uranium? The first part we'll go through faster than planned because it's straightforward and probably not imminent, while the second topic, in light of information revealed at this conference, may merit a closer look. these are the reactions possibly breeding fissile material. In both of them, there are available materials, and the result is fissile material that can be chemically extracted without any special isotopic separation. There are a number of routes for getting neutrons, and at the moment we aren't seeing a whole lot. I'm just, for the sake of completion, including like PN reactions and the high energy tritium reaction. And I understand that most of the time the tritium that appears doesn't seem to be coming from any high energy action, but there have been a few reports of the neutrons from high energy tritium colliding. So, for the sake of completeness, we should try to keep all the different possibilities in mind. The other things that are of interest are the transfer of neutrons, like in the isotopic changes that a number of people have had theories about in experimental evidence, and high Z reactions, which widen the possibilities of what may be happening and what reactants might be brought together. And also under other there, I'd include the Regev and Miley work on deuteron disintegration that they think might breed fissile material even in less than critical configurations of fissile matter. At the moment, those reactions haven't been very high, but they've been getting higher, and to get a sort of metric on this, what we should do is look at just how high the neutron flux would have to be for this to become an important issue. And the most straightforward way of doing that is to look at how high a flux you could get from the alternate ways of doing this, like from a reactor or from an accelerator neutron generator. The accelerator neutron generators have fluxes that are roughly around 10 to the 10th neutrons per centimeter per second. And so anything below that amount from cold fusion shouldn't be a concern to us, because it would be easier for people to simply use one of these very common techniques now of using an accelerator to generate neutrons through reactions after accelerating charged particles. And somewhere above that level, but definitely within or below 10 to the 15th neutrons per centimeter per second, you're sure that you've reached a nuclear proliferation problem, because that's the rate that you can get in reactors that can breed these materials. Where that level is something that might be debated depending on how large you want the thing to be or how quickly you want it to be doing the breeding. But those give us some solid numbers to look at as cold fusion improves. These are some of the signs that there may be possibilities for increasing the rates. Oh, and because obviously even the neutron bursts that we're seeing now are several orders of magnitude well below what we saw as that requirement to match the neutron accelerator generators. accelerator neutron generators. Most of these lines are self-explanatory, so I'll go through them quickly. What might need a little help? Well, you've heard plenty of people have theories about chaining. You've got Pedalence and J.C. Jackson and Takahashi, Case Becker, and just about anybody who has an explanation for bursts or large increases in the effect. Experimentally, I don't know if people have talked about this very much, that there's the God-Shani experiment where he aimed neutrons at a cold fusion experiment and got more neutrons coming out. They were stimulated by that, and these were of higher energy, and so they couldn't have been just from scattering of the neutrons. Also of interest is the signs of precursors, because say when the cold fusion reactions do increase a great deal, if we find ways of doing that, if there's still as much extra, just as much of a ratio of heat to the neutrons as we're seeing right now, then that would make equipment for this pretty untenable. But that's only true if you can't separate the heat from the nuclear reactions. And the experimental signs and the theoretical signs that there may be some kind of precursor to the cold fusion effect before there's a nuclear reaction makes it seem possible that we might be able to separate the two, so that the great heat might be somewhere else and the nuclear reactions take place at a different time or place from where all that excess heat is. And people along that line are like Dr. Lai and Rout and a lot of the soft X-ray evidence. And theoretically, the exotic chemistry folks like Brzezinski and Vigier and Barut have all been talking about things where there could be the heat caused by, say, a shrinkage of atoms or molecules, and mils too. And then possibly from that some kind of nuclear reaction after. To be fair, Mills has tried to separate himself completely from nuclear reactions. But this is just something that looks like a possibility to keep an eye out for. Lastly, I think that an important point is that the current level that we have right now is unexplained. And the levels that we have right now for a lot of the effects are 40 or 50 orders of magnitude above what you ordinarily would expect. And so just a few more orders of magnitude might be possible yet. And so what we should keep in mind is what we don't know can hurt us, and there's much that we still don't know about cold fusion. Pardon?
Sometimes what we don't know can hurt us.
So I'll get into that in a little bit. For the second part, the second concern about the possibilities of cold fusion making natural uranium breeders possible. For that, we'll look at G.F. Serafellini's experiment that was reported in the July '93 Fusion Technology as a technical paper. And while it hasn't been replicated yet, I haven't heard of anyone attempting replicating it. It looks like a very clean experiment. The most important thing about this is, very simply, he observed gas from a cold fusion cell that appeared to trap neutrons and then later release them. And this seems very peculiar, but what he did was he used a redox reaction generating HD molecules The reaction took place over about 200 to 400 seconds. He took these evolved gases from that reaction and sent them to a paraffin tank. And the paraffin thermalized the background neutrons so that the detector inside of the tank saw the neutron count within that region. When the gas came in, let's say that this is the level of the background that he was getting, background neutrons. When the redox reaction started, the neutron count went to 0 for a few hundred seconds, maybe a few blows. And when the reaction went to completion, the redox reaction, then the neutrons came back not up to the background level, but beyond it, like they were catching up, and continued for a little while, and then went back to normal. And the interval of this area and that area were about equal. He felt that he had a 4 sigma confidence that the neutron depletion during the reaction, during the redox reaction, and the neutron catch-up after the reaction were valid. And this flux reduction was very dramatic. It was about 50%, 40 or 50%. And by putting cadmium foil into that same region, he was only getting a reduction of flux of 15%. So he said this couldn't be any kind of impurities or anything. It's really a very dramatic effect. Now, Serafellini presents an explanation of this neutron trapping. He suggests that the redox reaction, like other cold fusion stimuli, form metastable molecular states of unusually small internuclear separations. And this internuclear separation, being near the wavelength of thermal neutrons, he feels a neutron could be trapped in these unusual molecules that he's proposing. And then they'd be trapped by Anderson localization. Now, a slightly different explanation, but with similar results, could be that the whole gas region with a number of these unusual sites could be causing an Anderson localization of the neutrons. And yet another interesting explanation appeared at this conference. Dr. Hideo Kazuma said that he showed that the interface between regions of differing internuclear separations may trap neutrons, so that at the surface of that wall, you may be getting a neutron trap occurring. But whatever the explanation, the experiment itself is very interesting. Now, if you take that idea of a neutron trap that releases the neutrons later, and imagine the effect of the neutron trapping in the following configuration. I wish I could use my hands.
Joseph, 3 minutes.
Okay. If you have a region of fissile material, and around that you put a moderator, and on the outside you put a region of this sort of neutron trapping gas that then flows continuously into the core of the fissile material, what you'd end up with is something that would never release the neutrons at the surface. And this would give you a very dramatic improvement in your criticality. Now, in that kind of condition, you could get a mass much less than what's normally required for criticality going critical. And in response to what you were saying, this would not be a prompt criticality, it would be a delayed criticality, so it would be fairly stable. The other implication of this is that natural uranium, unenriched uranium, could efficiently breed fissile materials. Ordinarily, the natural uranium, it comes so barely close to criticality itself that if you put the extra load of a lot of material to be bred, that absorbs and you just don't get criticality. But if you have this sort of efficiency, then something with just simple natural uranium at less than the amount of normal criticality may be doing your breeding. So I think that these hazards are possible if neutrons can really be trapped and released, provided that this can also happen at a high flux density. And very quickly, I'd just like to mention that Anderson localization explanation has a significance to all this, because it's also possible that because Anderson localization fails when the flux is very high, then if we examine this, we may find that it would fail because of that reason. If you try to get it up to where it was useful, the Anderson localization would no longer work and the trap would no longer work. It's like we've reached saturation. So these are, I'll just show you these. These are the things that I think we should be looking for as the improvements in cold fusion occur. Thank you.
Are there any questions? Yes?
I read in a French newspaper a few months ago there was some work in the former Yugoslavia about making plutonium with uranium in cold fusion. Are you aware of that?
That was, did you say in Yugoslavia?
Yeah.
Yeah, in the Figaro, yes.
Yes.
You could talk to Dr. Vigier about that, because I think he was quoted in that article. That's something that I was concerned about. Yes.
Awesome. Go ahead.
Quick question. Do you think that the lack of support for cold fusion by large nuclear countries may be related to the view that there may be a threat as cold fusion is some sort of bomb generator, and that's why we don't see a lot of government funds going in?
You know, this is a personal thing, and I don't want to get into the personal things, but actually I've thought about that an awful lot for a couple of years now, and kind of tried to examine motives and stuff. And my impression from thinking about it a lot is that no one's being deceitful or anything. I've kind of tested that hypothesis. They just don't believe.
Two more questions. I see two hands. Make them brief.
Excuse me. Do you have any data comparing, let's say, 14 neutrons versus 2.5 type neutrons with regard to radioactivity of stainless steel? Is there, can you make a comparison?
I'm not sure.
Long range.
In what sense?
The neutrons irradiating the, let's say, the vessel of a nuclear cold fusion device. Do you have any relative comparison to that type of thing?
Are you talking about other losses other than the loss at the surface?
Yes, I'm talking about neutrons coming through into the reactor, which in turn will make the material radioactive. And therefore you have a radioactive disposal problem. I don't know if my question is clear.
Maybe since there doesn't seem to be indication, do that later. Answer that one later.
Okay.
Any other questions?
You mentioned the work of mining and Roderick. I presume that's referring to the uranium mining in Gabon also.
That's an interesting thing that they did also, but what I was referring to is a paper on deuteron disintegration.
That's right. They measure depletion of the deuterium ratio in the alpha mine.
No, in that paper, I don't think they mentioned that. But go ahead. What were you going to say?
I was just going to say that I produced some evidence criticizing his point of view, and it's produced in the poster session.
Yes, sir.
I think we have one comment or question.
Just a real quickie. In 1989, it was rumored, emphasize that word, that the federal government was seriously considering putting a trap on disclassifying any cold fusion work because of the possibility of it being easier to create tritium. They weren't worried about the neutrons, worried about the tritium, as is well known, tritium being a component that makes an atomic bomb into a hydrogen bomb. And the nuclear power plant, the way they make tritium now, they're projecting something like a $2 billion new power plant that might be interesting to explore the potentials of making tritium in some of the cold fusion devices.
Yes, in fact, they've been looking at spending $9 billion on that plant.
Well, thank you very much. We will now have James Griggs from Hydrodynamics, who has a very interesting paper talk about excess heat, or possible excess heat.
First, since I'm new to this field of cold fusion altogether, I'd like to introduce myself to the ladies and gentlemen here and thank Dr. Fox and Dr. Nylock for inviting us and giving us an opportunity to come discuss with you something that we found back in 1986 and 1987 in the form of excess heat. As Gene introduced me, I'm Jim Griggs from Hydrodynamics out of Cartersville, Georgia. And I'm not going to talk about any of the theories of cold fusion. I'm not even going to theorize exactly on what we're doing. I'm basically going to just go through an explanation of two tests that we have conducted at the request of some of the people associated with your group in the last 2 weeks, and give you an idea of what we have seen since we invented a device called a hydrosonic pump back in 1986. The picture that I have here are two demonstrators that we have in our plant, and this is the pump itself. The theory behind this idea came into being along the lines of what would happen if you created a shock wave within a fluid. And physics tells you that basically that's the water hammer effect. There's a minute amount of energy given off in the form of heat, but it's so minuscule that forget about it in your calculations. Being kind of an inquisitive energy engineer, I decided to try to see what would happen if we built a device that could create millions of these shock waves of very short duration and generate the shock waves mechanically and just see what we would come up with. Our results were kind of astonishing to us. We built the first working prototype, the forerunner to the design you see here, back in 1986. And improved upon that prototype until 1987 when we witnessed excess energy production. And our calorimetry is very basic in comparison to what I've seen here at the show this week, but basically we take an electric motor and drive through a direct coupling to the shaft our rotor. There is an internal cylindrical shaped rotor within this device that has bores in it at specific angles and depths to create these shock waves. And we supply that with a fluid, in our case, standard tap water directly out of your tap or light water, and create the shock waves. The phenomenon came into being when we took an electrical measurement of the direct input into the electric motor in the form of kilowatts or kilowatt hours used, and compared that to the content of the steam coming out at the vaporization level directly from steam levels or from steam tables, and said, we're getting out more than we put in, and that's impossible. So we were kind of concerned about that, and it persisted to show up over the years as we built and improved these pumps and improved the devices. And a number of people had come, and engineers, physicists, just inquisitive people have been to our facility to look at the pump and say, you know, what are you doing? How are you getting this?
And we have not been able to define or explain the exact way that this excess energy has come about. And that if you take the mathematical equation from the amount of heat that should be put into the shock waves and even compare it to the fact that we're generating with the device that I just showed you approximately 7 million waves per minute, the mathematics, same as in your case, doesn't come out. You just don't get enough heat out to compensate or tell you where that energy is coming from. And as I'm sure most of you can appreciate, I've taken very much criticism over the year for even insinuating that I could get more energy out of a device than we were putting into it in the form of the electrical drive motor. In August of this year, I was given the article that appeared in the August issue of Popular Science. And at that point in time, reading that there were other people in the world that were accomplishing this excess energy effect, I got in touch with Dr. McCougrey, called Dr. Fox, called Gene, called Jed Rothwell, and anyone in that article that I could get in touch with to try to get information and help us determine what we were doing and if it was real. And we got invited to come to the conference here and take a look, and then of course when some of the speakers canceled, we were given the opportunity to come and present the findings. Some of y'all may have seen our little booklet that we placed out on the table that shows the results of these two tests. And very briefly, I'll go through the tests with you and give you an idea of what some of our calometry procedures were. We basically have put a combination of steam and hot water in what we call a separation tank. We placed a dial thermometer in the end of the tank and at numerous locations placed thermocouples in both the steam line. We have a combination of hot water and steam that enters as a mixture. And so we separate it in a flash or separation tank and take the steam out of the top of it. And we put thermocouples in that line. We have thermocouples in this tank. We put thermocouples here and set this experiment up so that we could take the steam, divert it directly to atmosphere, or put it into a barrel. And we've done the same with the hot condensate. And we've taken the temperature of the condensate before the trap here and after the trap and have the same configuration here. Real quick review of what we did. As you can see, there's a water hose that goes into the condensate supply feed tank here. We've removed that hose and put it in the top of the tank. Filled this tank and weighed the water on numerous occasions and had our scales verified to within a half-pound weight of 1,000 pounds. Then we bring that water through a circulation pump into our pump, drive it with an electric motor, heat it, and then put it into the mechanism. What we were asked to do was to take that setup and be able to monitor everything that was happening. So we took and put control valves in line so we could bring our system to steady state, putting the mixture here, taking the steam off, as I'll show in the next one, catching the hot condensate, measuring the temperature of it before and after the trap, but taking a barrel, a 55-gallon drum, so to speak, we put 200 pounds of water in it, brought the system to steady state, and fed all the condensate into this barrel. All the steam then, by the same mechanism, we were able to balance and control the exact temperature and pressure of this tank constantly, monitoring it with thermocouples in numerous locations, exhausting it to atmosphere until we were ready to start the test, same as with the other barrel. To put 200 pounds of water in this one and then put a valve so that once the test started, we could measure the temperature rise in these two barrels and calculate the mass increase and the rise in the water, and that would give us our temperature output of our device. We could go back and compare that directly to the input of the device in that we attached a Granite's 808 demand analyzer and a BMI 3030 demand analyzer, which monitored the electrical incoming power and recorded the incoming power in both kilowatt demand and kilowatts. And I realize that y'all been used to talking about watts, but the smallest unit we run runs a 40 horsepower motor. So our production output is not in watts, but it's in kilowatts. Our smallest unit produces an excess of around 30 to 40% excess, and we use a 40 horsepower motor to drive that. So basically, we're putting in about 32 to 33 kilowatts and getting out about 50.
James, sorry for the interruption, but just to emphasize, all of the energy you're putting into the water comes from that electric motor, is that correct?
That is correct.
Thank you.
That is correct. The only other energy source is the circulation pump that's down here to supply the water into our pump, and that's monitored by the Drainix also, if we choose to do it that way.
It's only about 8 horsepower.
This pump is a quarter. It's a quarter horsepower. This circulating pump, Dean asked what horsepower was in, it's a quarter horsepower. But basically what we do is we take the water out of that condensate supply tank. I've indicated that with the blue line, excuse me. We take the water from this tank and bring it and put it into our pump and regulate that here. All these notations are in that book. It'll explain the procedure exactly. We put it into our pump under a constant pressure and temperature, bring it out of the pump, and I've indicated the mixture line with the green representation to where this is a Spence control valve. This can be done with a Spence or by hand with a standard ball valve, where we control the constant input into this tank. We can monitor that with both pressure and temperature controls here. Taking the hot condensate off, this is what went back to drum 2. Taking the steam off, and this is what went to drum 1. And a better drawing configuration of that I did real quick yesterday when I found out we were going to speak. So if this was the flash tank, you see all of the water going to this tank and the rising mass, all of the steam going into this tank with the rising mass, and then those calculations were done based on the electrical draws recorded directly from our Drainix and BMI machine on the electric motor, and then the calculation of the mass input into the barrels. This is our calculation formula. There's nothing in detail about it. It's basically if you raise 1 pound of water 1 degree Fahrenheit, we figure we put 1 BTU into it. We took a conversion scale for a kilowatt hour, converted it back to BTUs, and all of our calculations are directly in BTUs of input versus BTUs of heat output. The results of the first test on a direct comparison taking into consideration no enthalpy or convection, conduction, or radiant losses at all showed that with the mass of water, as I said, we started with 200 pounds in each barrel. The temperature in both barrels were identical. Then we took the temperature rise of each barrel and came up with the total BTUs added to each barrel and the total BTUs added during the course of the test. The kilowatts hours that were recorded directly off the Drainix indicated a BTU output of the electric motor. So that gave you a direct relationship. What we call a COP here is just commonly in my business was called coefficient of performance. It was your energy out divided by your energy in gave you a coefficient of performance of how energy effective a building was. So we at home still use that. Our coefficient of performance on that particular test on just a direct relationship was we got 103% out for what electricity we put into the motor. If you go back and include that in the course of this 15-minute run, that the temperature of one of the barrels was such that when you take the total mass of water that was available and what was collected, we lost 2 pounds to evaporation. Actually, 2 pounds of the water evaporated and could not be accounted for in any other way. We added those evaporative losses back. That showed that we were 110% efficient. We went back and estimated the radiant convection and conduction losses of the piping, and that flash tank itself, added that back. It came to 114% efficient. Then we took the efficiency rating of the electrical motor as rated by the manufacturer. This happened to be a Lincoln 40 horsepower standard AC motor rated at 3,600 RPMs. I would point out here that this is the manufacturer's rating, and both the Drainix and BMI do record power factor. So power factor wasn't even taken into this consideration. If it had been, this figure would have been much higher, because at temperature we're not operating at the full load of that electric motor. But this specific test showed that we had, for 1 BTU in, we had 1.38 BTUs out. We did a second test that was very similar to this, and this was done with a little bit larger pump to show you the results, because we can produce hot water or steam with the device. The basic setup of this test was the same except for the end of the test and how it was run. The water mixture went into the flash tank as before, and the hot condensate was brought out and collected into a barrel. Once again, we set it up so that this barrel could be collected. We could exhaust everything to atmosphere until the test started, and the steam was exhausted to atmosphere continually. We had a fixed amount of water available in that supply tank to start the test, so we knew at the end of the test, whatever wasn't collected in this barrel had to have gone to steam. And we started the test, switched this valve off, this valve on, started collecting the condensate. Once again, we had all the thermocouples. As Dr. Morrison mentioned earlier, he said you should use more than one kind, so we did. We used thermocouples, dial thermometers, handheld thermometers. We've checked our calorimetry the best that we can at this point in time. At the end of that test, we converted it and broke it down into two different areas. We broke it into the measurement of the BTUs that went into the steam, and as I showed you from the chart previously, I took my BTU input content as 1,091. That's the difference in the starting temperature of my condensate water and the BTU, or the enthalpy of the water from the steam tables at that pressure, and counted that as my BTU input to the steam. I collected the hot water mass and took the differential temperature of the two, collected and counted that as my BTU input for the condensate. And once again, we did the same thing with the electric motor and drive system. We recorded the kilowatt hours used. And as you can see from all of our combinations here, the direct relationship on this one, and this was a 75 horsepower electric motor. The energy efficiency of this motor was a little higher. But our direct relationship, just the energy in, energy out, no losses taken into consideration, said that we got 118% of the energy out that we put into the electric motor. If you go back and add in your radiant losses, it came to 121%, and then taking into consideration the electric motor losses again, it was back at 138%. I did just a real quick graph to show you that in relationship to what we did, the input energy over the 20-minute run, starting at zero, where it came to, then the direct output measured energy, and then the true output taking into consideration the energy losses. I would like to point out also that we also have a device that produces hot water only. In this configuration, we didn't have time to complete some testing on this particular design, as this was new to us. But you can see here our BMI and our Dranix machines, and by the way, these were calibrated by General Electric just a couple of weeks before this test was taken. But in this configuration, we have a tank this particular tank has a total of 9 probes in it. So we monitor temperature location, not only going into the pump, coming out of the pump, but all through the tank. And we can put hot water or put water directly into the pump and take water directly off the other side. This particular system here was run with a 100 horsepower electric motor. But we have flow rates that, as we vary them with this, you can see a valve right there if you look real closely. And we monitor the flow rate with 2 different flow meters, so we know exactly what this supply pump is pumping. And our flows will vary between 5 to 10 gallons a minute with a direct delta T across the rotor of anywhere from 90 to 150 degrees. And the efficiencies on this pump show, on this particular one with the test we run now, efficiencies that range, not taking into consideration the electric motor or any losses, but they show efficiencies of like 0.9 up to the 1.4 range also. In the past, that's fine. In the past, I'd like to point out, and it is pointed out in the report, if you don't have a copy of that report, we'll be glad to get you one. because we had had so much controversy as you have about the fact that we were above unity, about 3 years ago, we changed the design of a system. And I'll put this back up to give you an idea of how we changed it. Our previous design, our pumps were a lot bigger than this. This particular pump would have been about half the length of this table with our rotor, our heat producing cylinder on one end with the seals, the bearing configuration, a long extended shaft to balance it sitting out on the other. Those pumps were very hard to disassemble, very hard to work on in the field, so therefore, from a maintenance standpoint, we were asked to make some corrections. We have that at the plant. Those pumps produced an excess energy in the 2-to-1 and better ratio continually. When we changed our design of this system, we actually hurt ourselves on the efficiency of the system because we changed the location of our input where the water goes in and where we take the steam and water off. And it seemed to affect the production of the pump in that, as I mentioned earlier, now we have a combination of water and steam output. We seem to be sucking water through the system, where with the older pumps, we're putting out a steady flow of steam with no water mixture in it. As I mentioned at the start of the talk, we have been doing this since 1986. We are a commercially viable company. We've actually sold pumps that are out in the field, and we have pumps in place that have been there going on 2 years now in operation, and have effectively replaced gas-fired boilers in a relationship. As all of you know, you have to have a 3-to-1 relationship to make that break even. But because of our instantaneous regain time on the not having to maintain that water over a 24-hour period of time, we've been able to replace gas-fired boilers in 2 locations and keep their utility cost level at the same thing it was prior to us going in and replacing that gas-fired boiler. We have had numerous people come in and conduct tests. We put these things out in the field, have them operational. We don't know exactly why we get this effect, but it sure did make us happy to hear that some of y'all had gotten the same effect in an excess energy situation. And to quote what somebody else said to me, it made me feel good to know I wasn't the only idiot in the world. From everything we've presented to you, we've drawn 3 conclusions about our company and the things that we've seen here, and we've really enjoyed being here for the last 3 days. Based on the present test results that we have and the test results that you've just seen, we do believe that there is excess energy developed by the hydrosonic pump. We've not reached our final conclusions as to the process or processes that are creating this excess energy. But our pump components and specifications are similar to those necessary for the production of excess energy, as explained by many of you during the course of the past 3 days. And we plan to intensify our research and develop with the development and assistance of individuals and institutions within your group that might help us to come up with an explanation as to where we're getting this excess energy from. Thank you.
Yes, I'll make a comment and I'll question now.
During the past 8 months, I was asked to edit the New Energy News. And it's extremely interesting because we have found there are a great deal of anomalies like this in various parts of the world. A fellow in Colorado by the name of Firewaltz sold his company to HP and got quite a few $1 million. So he financed the getting together of about 20 of these screwballs like myself and you don't mind this gentleman here that have been involved in some of these peculiar items. Now, just for your information there, I think you probably already know about this. There is a German book that had been published several years ago on vortex flow, in which this book claims to have, with vortex flow, you can get excess energy. I met a gentleman in New Mexico who was in the process of moving to Arizona, Mesa, Arizona, and I haven't gone down to visit him yet, but he claimed to have a turbine, let's see, a turbine driving, what's the generator with water and the pump, what do you call them now?
Heat
No, not the heat pump, it's just the, anyway, one's the driver and the other is the one that does the work. I'm sorry about that.
Compressor?
Hydraulic generator. Okay, all right. He had it rigged up in such a way that he was getting enough excess power so he could take the extra energy of the water, come back and drive his water pump and still be putting water out there to the main. Now, I was director of the first research lab at the University of Utah Research Park, and our studies was in fluid dynamics. Our group was the second group after the Naval Research Lab in Washington, D.C. to solve the Navier-Stokes equations via computer for the fluid flow. Many of you will know Navier-Stokes equations are nonlinear partial differential equations. And so anyway, this to me is very fascinating what this gentleman has done, but it's not without precedence in the sense of having been reported in the screwball literature. None of this has ever been reported in peer-reviewed literature.
I'll be glad to answer any questions. I would like to point out one thing that I didn't cover in my presentation. When I set out to develop this pump, I knew nothing about the field of cold fusion. And this is about 9 years later, and I know nothing about the field of cold fusion today. It wasn't built as a cold fusion device.
Two questions. That gentleman there first.
You showed a slide on efficiency versus time. Why do you get no difference at low time, a large difference at long time?
Well, it's not that I get no difference at zero startup. That was just a reference point that I used to start to show that we ran that test for 20 minutes and that I was showing zero input to the motor and zero output from the unit because I was exhausting the steam to atmosphere.
One more question.
That was energy, by the way, not power.
Pardon me?
That graph, if I was not mistaken, was energy, not power.
Did you consider the amount of energy in the water which is in the tank when you started?
Yes, sir. I took the BTU content of the 200 pounds in each tank and subtracted that as far as the BTU level of the input from the output of the unit, and that's where I came up with the BTU input number that I have.
Somebody has to ask about the insides of the contraption. But I'll start that by observing, I think you said you had 7 million shocks per minute, and if the rotary speed is a few thousand, then 3,500, so that figures out to be about 2,000 shocks per revolution. Implies a very interesting design, so I'd appreciate whatever you could say about the inside of the machine.
It is by the way, I don't mind talking somewhat about the inside of the machine because we do have a patent that's already been issued. We have numerous patent applications that are still pending, but the device and the process is patented. The design of the rotor itself happens to be cylindrical in that it's, in the particular ones that I've shown you, were 12 inches tall as far as the diameter in relationship to the actual shaft that goes into it, and 6 inches wide. And there are numerous holes bored in that at specific angles and depths to create the shock blade. And how we calculated the number of waves, it was the distance that the water had to travel to reach the extinguish point of one of the bores in the cylinder, and then regain to start the process over again, spinning at 3,500 RPMs.
Should be measurable also.
It may be. You know, a fluid dynamics engineer, we hope, can tell us a lot more about this as we go along.
Are there any other questions or comments? I might make a comment or two myself. I've been so fascinated by this myself, and have come up with a number of ideas, and maybe it will stimulate some other discussion. Due to the fact that this room nominally is available until 6 o'clock, by the way, not that you have to stay. But one thing that could be done is to dump a kilogram or so of heavy water in. Another thing that can be done is to coat the entire innards of the system with a plastic or Teflon or something to prevent any contact of the fluid with the metal in the rotor system, to find out whether the metal is required. Other things would be involved, might be plating the rotor with palladium or other materials. And those are just some initial ideas that I had, testing the water.
This work looks a lot like the ultrasonic work that's been done with piezoelectric, whatever. So is there any damage to the surface of your tank or your tubing? What's happening after some time?
No, that's been one of the unique things about the device that we have seen, and we have speculated is because of the dynamic viscosity of the water. When it shears, there's a film layer that's created generally around the housing, around the rotor, where the holes or bores are not drawn. We've got pumps now that have been run continually for over 3 years, and there's no degradation to the rotor at all. There's no corrosion, there's no wearing to it, which surprised us. And there's been a number of solutions that have been run through these pumps. We did not just run tap water or light water through it. We took a pump and went to Fort Lauderdale, Florida about 4 years ago and got ocean water to see if we could distill water and see what the effects would be on the pump. And we ended up with a concentrated salt solution in pure water. And there was no damage to the rotor or the interior housing of the pump at all. There was some damage in that particular test to the seals, but that was because at that time we had a seal configuration that wasn't stainless. We run antifreeze through this pump, used antifreeze that come out of a car and have been able to reconstitute the ethyl glycol from the antifreeze and boil water off of it. We run caustics from the textile industry through it to see what we can do about concentrating pollutants that normally go into our rivers and streams, and ended up with a clean water from the steam boil off and a concentration of the caustics that come from the textile industry.
Do you try alcohol or anything like that instead of water?
Not yet.
The acid test would be what Morrison said about closed cell calorimetry. Put your whole thing in a room that's totally sealed except for your electric power cord going in, and measure hot water coming out or something, and that way there's nothing that you're overlooking, because there could be an effect that you're overlooking in your theoretical analysis. I was interested in solar energy, and I knew a man who was perfectly sincere, and he was put out of business by a government agency that said what he was doing was physically impossible. And about 5 years later, I read an article that showed that if you put a duct from your roof down to your floor, and you sucked the air out of the ceiling and blew it in at the floor, it reduced your heating bills 30%. And so there could be some external effect that you never thought of in your analysis. So the only thing that is going to be an acid test is a closed cell calorimetry.
Are you volunteering the lab, Dr. Bates?
No, that's the problem. I will write a letter to Oak Ridge or Los Alamos and hold over the National Bureau of Standards and say the reward to risk ratio is so high they ought to test it. But unless it's tested like that, there's no point in speculating whether it's real.
We totally agree with you, and if you get a copy of the written report, you'll find an author's note in there that we invite anyone, as far as skepticism, input, visit our plant, assist us in any way you can. We're very open to those suggestions, and we hope now that because of some of the things that we found here, that we're going to be able to do some of those type testings. As a matter of fact, Gene, when he found out about the device and reviewed some of the preliminary literature that Jed Rothwell had come over to our plant and taken, Gene has suggested getting this to some specific laboratories and is making some recommendations to do that, and we do intend to do that. I would like to add to that what you said about bringing the heat down. My background is in energy conservation. For 15 years, I was an energy engineer specializing in the field of energy conservation in industrial commercial buildings.
One thing I might say, in light of what Bob said, I think Bob's idea of making a calorimeter on it is excellent. However, I think in a way it's already been done, and maybe you could describe this. You have results from the heating of the whole building, which is in effect a calorimeter. How's that for the...
I didn't show that because most of the time when we show that to engineers, but we've taken one of these pumps and hooked it up with a conventional water-to-air heat exchanger for hot water heating of a residential home. And we heat a 7,800 square foot building with a 7.5 horsepower electric motor in the winter. Thank you.
Can I show you a little, excuse me?
I want to just ask a short question. You're planning to do big machines. Are you planning to do small ones? Is it easier to make calorimetry experiments and things like that instead of having a big tank and completely expensive materials?
The answer is yes. Right now we have rotor designs that go from 4-inch rotors all the way up to 20-inch rotors, and we actually have a prototype for what we consider a 24-inch rotor that would be 12 inches wide and would be the equivalent of a 200 horsepower gas-fired boiler. As you know, a 200 horsepower boiler would be about the size of this room, and our pump's about the size of the top of this table. But yes, we have built some smaller ones. The only problem is to create the effect, you have to spin them at such high RPMs that we tried to settle on a standard off-the-shelf AC motor spinning at 3,500 RPMs for economic purposes.
Let me discuss with you just very briefly. This is this is a nozzle in which a compressible fluid would be put in, such that this pressure is considerably higher than the atmospheric pressure. You get a shock structure. This is what you see after with a missile going up in the air. You see this diamond shock structure. But this structure, which is called the Riemann shock, if you put a hypodermic needle right in here, you can move that hypodermic needle just a very small fraction of an inch, and the pressure out here that you put onto that would, for example, if you're using 100 pounds here, the pressure there would go from say about 5 pounds on one side to about 95. So across a very small boundary, they're just really few molecules thick. That Riemann shock is supporting a pressure difference of 95 to 5 pounds. A fascinating effect. So what we did, we made a device that you could put a little air, blow a little air here, and you could move that shock structure, and we were able to make a no moving part valve that would switch from like 5 pounds to 95 pounds with just a little bit of pressure here. Now we went to an incompressible fluid to see what could be done with that. What we found out was that if this again is a nozzle here, this comes out under certain, I've forgotten the parameters now, but under certain configurations, as you let this go into, this is what's called a submerged jet, you let it go into a reservoir, then under certain pressures, this thing comes out a ways and then just bursts into cavitation. It just fills that area out there with vapor of whatever the fluid is. We work with hydraulic oil. The same thing would work with the water. We found out in the same fashion we could put a very small signal there, change where that cavitation was occurring, and again we developed a incompressible fluid, no moving part valve that could switch relatively high pressures to relatively low pressures without any moving parts. I'm suggesting that the very complex nature of shock structure and cavitation in here that you're enjoying with the way you've been doing your work. You're going to make your steam here in a sense by this cavitation if you don't let it collapse back in again. I think you got an extraordinary interesting effect, but I think it has absolutely nothing to do with cold fusion. I think what it has to do is that you've got an anomaly here that's absolutely different than anything, an anomaly in your pump, not in this, that's absolutely different than reported in the literature. So whatever that idea is worth.
Can I have your drawing? Yes, sir.
On the
It's a 15-minute time limit, yes, sir.
So if you reported it at 7 minutes, it would be less.
No.
That was backwards. I think that was.
Okay, that was confusing.
No, in 7 minutes, the efficiency would be basically the same. On our direct pass inputs, where we calculated on the last slide of where it's just water delta T across the rotor, we calculated on 15-second intervals.
Are there any other questions? If not, we probably conclude. Any others? Or just talk privately. Thank you very much. I might just put in a plug for Dr. Schwinger's, Nobel laureate Schwinger's talk, which I will give. At 6:30.
Oh, really? How come that wasn't advertised?
Well, it was. They just put up.
Swinger's talk was never advertised.
Well, Swinger himself.
Schwinger's not here. I'm reading his talk.
Fantastic. How come that wasn't in the program?
Well, he doesn't appear until late.
Yeah, well, I read about it.
Exactly the nature of what it is.
What program is this? Is this B or C? It's in D. I believe it's in D.
When they handed out the stuff from the registers, was it just what
Came later.
is this the first time we were told about it?
No, this
No,
morning
it
they
was
showed
told
this.
this morning.
Oh, okay, okay. Well, fantastic. Glad you mentioned that.
Very impressive. Yeah. I don't see the mistake.
It's definitely going to be shipped up MIT.
I hope so. In the next couple of weeks.
I want to make sure I got a copy of you standing there. So I don't want a copy of the video, I want a copy of you standing right there.
Why? The whole time?
No, just, no.
You in the back of my head?
Turn this off.
No, I know.
What?
No, I haven't turned it off yet.
Oh, yeah.